Hi, everyone. Well, I'll quickly go through these since we're a little bit low on time, but there's a few announcements we wanted to make before Umberto's talk. We are taking a brief hiatus from the seminar series in December and January, and we'll be picking back up in early February for our next seminar series. We'll have the seminar schedule updated. You can find that online at the URL at the top of the page there. And then if you haven't already, please sign up for our mailing list. We're up to 170-ish members now, which is really exciting. And like we do with most talks, after this one, we will post a recording to our YouTube page. So please feel free to check that out as well if you'd like to come back and re-listen to anything that Humberto has been talking about. And then quickly, what we also wanted to mention is that please save the date for our upcoming workshop this summer, which will be held in around late July in Neustrelitz, Germany. We will be sending out a Google form to our mailing list soon, with just a couple of quick questions about registrations and online or in-person attendance and so forth. So if you haven't signed up for a mailing list, please do so and respond to that into that form in the future. So I will cut our announcement short there, but we're extremely excited to listen to Humberto now. So I'll pass on to Anthony for a quick introduction.
All right, thanks, Adam. Hello, everyone. As usual, please keep yourself muted. Today we'll save questions till the end, and feel free to raise your hand or enter it in the chat, and we can ask for you or call on you, but we'll save questions till the end for today. And so today we'll be hearing from Humberto Godinez. He's currently at Los Alamos National Laboratory and has a background in data simulation, sensitivity analysis, uncertainty quantification, and large-scale computational fluid dynamics, including space or Earth weather, and maybe even now space models too of this current talk. So thanks very much for joining us today, and feel free to get started.
Okay. Can you guys hear me? I don't know if I'm muted still.
Yeah, sounds good.
Okay, perfect. Again, I apologize. This was a little bit embarrassing. I thought it was 11 Mountain, and it wasn't. So let me just share my computer. Okay. Please tell me that this is correct. Wow. Yes, please share my, 1 second. It's asking me to authenticate. It doesn't believe that it's me. And it's telling me, okay, can you authenticate? 1 second. Okay, I'm gonna have to close this so I can actually, the Mac OS is telling me that I have to quit Zoom and then go back in so I can share my screen. Is that okay?
Yes.
Okay, we'll be right back.
All right, looks good. We can see them now. And I think you're still muted.
So here I am talking to myself, getting all excited, and nobody's listening.
Okay.
Sorry about that.
Good to go.
Okay. Thank you very much for this invitation. I really enjoy actually giving these type of talks in data assimilation. I've been keeping track of this group for a little while, but it's pretty exciting to see people coalesce now on this very interesting topic, which is data assimilation for space weather models. I've worked in space weather models for quite some time. I've done everything from, well, not everything, but I've done radiation belts, I've done ionosphere thermosphere, I've done ring current models, and a little bit with the BATS-RS, which is the magnetohydrodynamic code, which is very interesting. And in here, I'm going to actually show, also the solar photosphere, which is a project with AFRL. That was pretty interesting as well. In here, I'm going to talk about the data assimilation for the ring current model, specifically the RAM-SEB model. This type of models have, let me give a little bit of an introduction. So data assimilation was basically first developed for atmospheric weather models, which follow very much a fluid dynamics type of behavior. And when we're talking about space weather models, they're not always behaving like fluid dynamics. They behave very not strange, but very non-fluid dynamics way. And RAM-SEB is one of these models. It's very interesting. It's a ring current model that actually tracks particles all along the Earth magnetic field. And I'm going to talk about what I did for this data assimilation and what are the challenges and how I actually overcame them. So let me see if I can move there we go. I don't know if everybody can see that. So the first method that I tried for the ring current model is basically this Ensemble Kalman filter. This is a method that is very popular in the community, both because it's very easy to implement, right? So essentially, you are assuming that the model and the observations both have a Gaussian distribution, right? So if it has a Gaussian distribution and you want to actually compute, say, the correct distribution or probability distribution of your prediction, you basically implement a Bayesian approach where you combine these two Gaussians. When you do the Bayesian approach, you get the Kalman filter analysis equation, which is this equation right here, equation number 1. And it's essentially you're updating your forecast with a kind of a correction term. And it's weighted by this K matrix. The K matrix is the common gain matrix. And that is basically telling the update how much you should trust the observations and how much you should trust the previous forecast, which is the XF. The easier, why people actually gravitate towards the Ensemble Kalman filters, because it's very easy to implement. You essentially you model an ensemble of solutions from your model that will give you a description of what is the mean and the standard deviation. In other words, a description of the Gaussian distribution, assuming that that's correct. And also, assuming that you have a Gaussian distribution in your observations, that also has a mean and covariance matrix. Once you have that information, you basically implement equations 1 and 2. And in here, each one of these components, YO is basically the observation vector or observation variables that you have. The XF is your model solution of what those observations should be. And the H is essentially an observation operator saying, where do I have observations in the whole model solution, right? And in here, K is essentially the common gain matrix. Now, the common matrix is composed by H, which is the observation operator, P superscript F, which is the covariance of your model, and R, which is the covariance of your observations. Here again, I'm repeating this many times, but both model and observations are assuming to have a Gaussian distribution. That means that you can describe that probability distribution through the mean and the covariance matrix, right? And if you see the common gain matrix, you're basically dividing your variance in your model over the variance assumed in your model and your observation, right? So it's a weight that tells you how much you should go towards the observations or how much you should go to the model. And the covariance is kind of like a measure of sensitivity, or if you will, uncertainty in your model and your observations. So this is all there is for the Ensemble Kalman filter. If you actually just implement it straight out of the box, if you will. It's just equation 1 and 2. Once you compute your Kalman gain matrix, you do a weighted correction of your forecast or your model solution, and that's your analysis XA. And the analysis basically is a new estimation of what is the actual mean of your probability distribution of your event of interest. In other words, where it should go. In here, the one thing that makes the Ensemble Kalman filter different from the regular Kalman filter and extended Kalman filter is how you approximate that covariance matrix. And in the Ensemble Kalman filter, as the name suggests, you're basically simulating an ensemble of model solutions, and you're computing this covariance matrix of that ensemble that you actually computed. And it's a very simple formula. Everybody knows the formula of the covariance matrix. And right off the bat, you can actually see something that is interesting. In many models, even in RAM-SCB, we're talking about tens of thousands, sometimes hundreds of thousands of variables, right? And if that's the case, you can essentially vectorize that thing, and you can have a vector of, say, 100,000, right? You can imagine that the covariance matrix of a vector of 100,000 is going to be 100,000 times 100,000, right? This is a really, really big matrix. But if you approximate it through the ensemble, right, you have to be conscious of how many ensemble members can you actually simulate. In this case, in the Ensemble Kalman filter, given that the models are really large, these are very large dynamical systems, you cannot assimilate maybe more than, say, 50. Maybe you're very, very efficient and you can simulate 100 model simulations, right? So 100 is definitely a lot less than 100,000. So you can see already that if you approximate your covariance matrix with only 100 ensemble members, right? This is 100,000 by 100,000 matrix. That matrix is going to be incomplete, if you will. It's not going to give all of the correct correlations between the variables in your model. And all of the versions of the Ensemble Kalman filter is trying to make that covariance matrix of your model more regular and correct, essentially. So there's various methods to basically regularize this covariance matrix, everything from local Ensemble Kalman filter, transform Kalman filter. All of these things are trying to make the covariance matrix of your model essentially more correct. And there's various issues of this thing. Okay, so that was the Ensemble Kalman filter. This is the method that I'm going to actually implement to the RAM-SCB. And in this case, this is the actual algorithm that I actually came up with to regularize my covariance matrix of the RAM-SCB model. So essentially, think of, I define a matrix, capital X, and I stack essentially my ensemble members from 1 to n. From that matrix, I compute the single value decomposition, or think about the proper component analysis, PCA, right? And I define this new basis, which is orthonormal to where the model is varying. And here you can see this single value decomposition, U sigma V transpose. And my basis is essentially 1 over the square root of n minus 1, U, my vector, my orthonormal vectors of this ensemble, and sigma, the single values of this ensemble, right? So when you actually use this B matrix, which is defined by the left single vectors and single values of the SVD, you essentially project your ensemble into a space where you see the model varying the most, essentially, right? So you have this regular space of where your ensemble lives, and then you project it to say, look, these are the directions where I know it's going the most. When you actually use this matrix B as a projection matrix, you're going to use B transpose B inverse, right? And that's going to give you essentially a weight. In other words, that's the ensemble member Xi is going to be how much weight is there in this ensemble member of the most varying directions. This might be a little bit confusing, so I'm going to pause here if there are any questions right now, because the rest of the analysis is going to depend on this projection right here. I don't know if anybody has any questions whatsoever. Not yet. Okay. So just to recap, I'm going to use Ensemble Kalman filter, and I'm going to project my state vector into the weights of where this ensemble is varying the most. And I'm going to reformulate my Ensemble Kalman filter now in this space, in this new space of WI, essentially. So,
Humberto, so hold on. So do you compute this basis prior to your experiment, or
prior to the experiment, in other words, prior to doing the EnKF analysis? Yes. So this is basically, once I have my ensemble, I stack it, I do the SVD, and I define this basis matrix B. Then I basically project all the ensemble members from X1 to Xn into the basis, and that's going to give you a projection weight WI. So instead of having Xi, I have W1 all the way up to Wn. From there, now I have my weights, and I'm going to basically project observations into that space and do the basically the Ensemble Kalman filter in that weighted space. Once I have the, say, the correct weights, if you will, I project them back into the original variables. So that's what I'm doing.
So let's suppose you have 100 members and then you have 100 subspace, but ordered with respect to the singular value variance.
Yeah, exactly. And one of the advantages of this method or this approach is that you don't have to take 100 weights, because maybe only 10 to 15 weights are the ones that are, 10 to 15 directions are the ones that are varying the most. The other ones are going to be very, very small. So maybe you only need that matrix B. You can see that there's a U sub K, sigma sub K. That sub K is how many directions are you going to consider? And I can consider anything from 10 to 15. So in other words, I truncate it and say, the other ones I'm just not going to care. I'm going to care on these directions. What is the ensemble telling me? And that's what I'm doing in here. I don't know if that.
Yeah, thank you. Yeah.
Okay. So now, once I have that, one of the techniques that is being used in the Ensemble Kalman filter community is this localization and inflation. And this is essentially to remedy the covariance matrix, right? So when you have a covariance matrix that is not defined by, or completely defined by all of the variants that you see, you basically have these, what they call spurious cross-correlation terms in that covariance matrix. And that's saying these two variables that are not supposed to be correlated are going to be assumed to be correlated because the matrix doesn't have the full information. So when you have this artificial correlation in the matrix, and you do your update, really strange things happen, and unphysical or unrealistic solutions pop out of the Ensemble Kalman filter. So basically, you want to avoid those spurious cross correlations, and that means that you have to understand what the model is actually doing. In this case, for this RAM-SB, it's a ring correct model, right? So there's certain diffusion around concentric diffusion and a little bit of diffusion in the radial direction, right? So in here, the main assumption that I'm doing is saying, I'm going to assume that the correlation that is concentric is non-zero. In other words, there is correlation concentric, and the correlation that is in radial direction, it is still non-zero, but it's not, it's not going to be like the all the way to the outer ring. It's strongly correlated to all the way into the inner ring. That's not true. I'm going to say, look, I'm going to limit how much correlation there is in this direction. So that's basically what I did, and well, I'll show you the results. It was a good assumption, and we got physical solutions from the Ensemble Kalman filter. Another thing from the correlation matrix is that you want to avoid what is called ensemble collapse. And the ensemble collapse happens when you apply your ensemble common filter equation, and all of this, it does happen, all of the solutions, all the ensembles are almost the same. In other words, you converge towards the observations, but you basically kill the spread of your ensemble. And then all of your solutions are basically the same. And once you want to do the ensemble common filter again, it gives you errors, right? Because now every single ensemble member is the same, so your covariance matrix is almost zero. You don't want that to happen. So in here, to avoid that ensemble collapse, you have this ensemble. You can do covariance inflation or ensemble inflation. In other words, you add variance into your ensemble once you do your ensemble common filter or you do the analysis. And these are the two main remediation strategies for the covariance matrix. So let me just continue. So we consider all of these two things once we actually do our ensemble common filter for the RAM-SCB. And here what we did, so once we have all this set up, we have the projection, we have the localization, and we have the inflation, we basically set up the experiment for the RAM-SCB. And in here, we're going to do a very simple RAM-SCB simulation, which is a dipole magnetic field. We chose the July 18th, 2013 as the day where we see a substorm and within the data of the LANL probes, right? So we see this proton flux, we see a substorm that day, and that's the data we're going to simulate and assimilate. In here, I'm assimilating every 5 minutes. So we do the simulation of the RAM-SCB, and every 5 minutes of simulation, we do assimilation, right? We actually get LANL probes proton flux into the RAM-SCB, correct the state, and then restart the simulation. And the assimilation is done in logarithmic space because it turns out the proton fluxes and electron fluxes within the RAM-SCB, you have a very large scale of variance of the values, everything from e to the +1 to all the way to e to the -10. So if you try to do the ensemble common filter, do the assimilation within the actual variables of these large scale values, it's incorrect because, well, not incorrect, sorry. It introduces too much errors. So once you do this in log space, it actually takes care more or less of those length scales. And now you're dealing with numbers of order 1, everything from +1 to -10, right? And that's more amicable to what the ensemble common filter can do. For the ensemble common filter to generate the actual ensemble of RAM-SCB simulations, we are perturbing the initial condition with a Gaussian distribution. And in here, we used 30 ensemble members for the RAM-SCB simulation. And we did the assimilation, as I said before, with this SVD EnKF we developed. Any questions right now? I threw a lot of things right now. I don't know if anybody has any questions or wants me to slow down. No? All right. Okay. So let's see what happens with our experiments. And here what you're seeing is this unidirectional differential proton flux at a pitch angle of alpha of 90.0 degrees. And you can see in here how the proton fluxes, this is the energy spectrum in the y-axis and time in the x-axis. The proton fluxes are in this unit centimeter. Anyways, it's in these units is right here. And you can see that they vary from 10 to the 0 all the way to 10 to the +5, right? So they have a really large scale variation. And this is again July 18th to 2013. And right here around hour 15, you can see this perturbation of the substorm coming into the ring area of the LANL probes. This is the actual event of interest that we would like to see how much we can correct. You can see also some perturbations here at 21, and mostly on the beginning of that day, I would say it's calm. There's not a lot of perturbations going on. So we're very interested in seeing how the ensemble common filter with all these SVD can react to this substorm happening around this hour. And here, the top one, sorry, I didn't specify this. The top one is the Valorant probes A, and the bottom one is the Valorant probes B. They're slightly, when you look at these satellites, they're just slightly separated, and they are really good because you have observations almost from the same event at slightly different locations. So this is a really good data set, the Valorant probe data set, but I think you guys are already familiar with this. Okay, so we're going to assimilate this data, the proton flux, into the RAM-SCB and see what we get. And this is the results that we get. In here, what I'm plotting is the flux, the spin average proton flux for the RBSP or Valorant probes B for this energy bin. I could choose any other energy bin. I've noticed that the Valorant probes, when the energy is very, very high, you have a little bit more error. And when the energy is really low, you have information, but you don't have that much information that is of interest for us for the RAM-SCB. And here in the right plot, you are seeing the actual trajectory of the satellite of RAM-SCB, Valorant probes B, and you can see where it's located as I'm taking the snapshots of the data, right? So here we have energy 62, 97, and 133 keV. And here what I'm showing is the red line is the RAM-SCB without data simulation. The green line is the actual observations of the Valorant probes B, and the blue line is the solution of the assimilated observations. And here at the very beginning, I don't know if you can notice it or you can see it, both blue and green, in other words, non-assimilated and assimilated solutions are basically the same, right? Right here. You can see that the observations are all the way up in the space of the solution, the value of the solution of the protons. And we are starting essentially in the same locations. Once I start the simulation and do the assimilation every 5 minutes, you can see that there's a very drastic change in the RAM-SCB solution, where it basically tries to converge very rapidly to where the observations are. And this, you can see it in all of these three energy bins. Once it converges to where the solution is located, it almost tries to track almost on top of what the solution is what the observations are. And we can see right here in the observations, the green line, the little substorm right here, right there. We were excited that the RAM-SCB data simulation solution tracked the observations quite well. We were not able to completely reproduce the storm. We were within the neighborhood of where the storm happened, but we couldn't get that little bump, that little perturbation. By the time the RAM-SCB simulation ends, we can see that it tracks it really well here in this low energy, but then it kind of deviates in the high energy. And again, here you can see in the green line, you can see the little bump of another perturbation, solar wind perturbation. This is a little bit perplexing because I'm tracking the solutions, the observations pretty well once I start my final cycle of the Valorant probes, and then it actually deviates. And this is a little bit perplexing to me. We were trying to figure out why that happens. We can see that in both energies 97 and 133, it tracks reasonably well on energy 62 keV, but not on the other two. And I'm still trying to figure out why that is, whether I actually lost some kind of information when I imposed the projection to this weighted space. So these are the solutions. We're kind of happy that we have a good track, but we do have deviation from it. And in here, I'm basically giving you the root mean square of what is the non-assimilated solution versus the assimilated solution. In other words, we did this kind of validation where we assimilated Valorant probe A and validated with Valorant probe B, right? And this is basically what you're seeing. The non-assimilated solution basically has a lot more error versus the assimilated solution. And you can see again, at the very beginning both have the same RMS here at the very left, and then the RMS of the assimilation actually drops down. So that's basically telling me it is working. I am getting closer to the observations. At the very end, you can see this RMS of the purely RAM-SAB simulation drop down, and for some reason the assimilation, it's going up. And this is again reflecting a little bit what we saw right here, where the observations actually went down, but my assimilated solution didn't. So it's actually I'm still trying to figure out what that is. This is basically the figure. How does this look like in the actual ring current configuration? And here in the left, you see the pure model, and in the right, you see the assimilation. You can see that I'm plotting 2 points there, Valorant probe A and Valorant probe B. And you can see that there's more activity, way more activity in the assimilated solution than the not assimilated. Not only that, but you can see the perturbation actually evolve in the assimilated in this region, right? So it's actually doing what we expected it to do, to actually look at this perturbation. And we captured some characteristics of it, but we didn't capture the complete substorm. So that's something that we're trying to figure out. The RAM-SAB model does a good, you can see the perturbation right here in the boundary, but this one has the perturbation propagating inwards from the RAM-SAB domain. That's all I have right now. We have this assimilation in Python. It's a Python based, and we're actually porting this into the RAM-SAB open source code. We wanted to turn on the self-consistent V field, and we're going to try that actually in our next experiments. We haven't done it. And here we just assume a very simple dipole. And we have a couple of shield challenges that we wanted to actually, couple RAM-SAB with data ROS and do the assimilation in RAM-SAB and see what it does. So we wanted to actually do that. And do the assimilation for the electron fluxes, not only the proton fluxes. And that's all I have right now. I'm not sure what time it is. Yes, okay. I have 10 minutes. Thank you very much for your time. Hopefully this was useful.
Thank you, Humberto.
Thank you.
Yeah, it's a very interesting work. Yes.
Yes, it was.
Yeah, thank you for leaving time for questions.
Yes, sorry, this was.
It's an amazing work that you did. Okay.
Yeah.
Anthony, Adam, do you want to?
I guess we can ask the audience first if there are any questions they'd like to ask Humberto.
I have a question. For slides, I think 7 and 8 for that like periodic structures, is that like the, I guess the orbit, is it passing through like the same region of the LANL belt?
Yes.
Okay.
Yes. So here at the left side, I'm plotting more or less what is the cycle of where the Valorant probes were cycling, right? So in one day, it actually goes through that track several times. In this case, almost 3 times. And in here, I really don't. I'm pointing at with my finger, and I think you don't see it. So in this region, as I said, it got close to the, here's what I'm plotting in here. It got close to the outer region of this track around here. And I'm not sure what happened that the observations went down, and I was expecting the solution to actually track it, and it didn't. And I'm not quite sure what it is. Maybe it's because my assimilation, when I project to this, the direction of maximal error growth for the ensemble, maybe that space is not the correct one for the observations. So I'm thinking that's the case, but I'll have to do a couple more experiments and see if that is the case. Did I answer your question?
Yeah, pretty much.
Okay.
Thanks.
Yeah.
I have a bit of add-on question to just exactly the point that you're making. So you said this is a substorm, right?
Yes.
So then so you said that you created a basis using singular value decomposition prior to running this experiment.
Yeah.
Did that, so those ensemble simulations, like 30 members of bachelors?
Ramesses, not Patsaras, only
Oh, okay.
Ramesses.
Okay, so did it include a substorm in one of those 30 runs?
Excellent question. It didn't. So when we looked at the ensemble, I do see, like I said, let me just, I don't want to move too fast. So I do see that substorm essentially brewing in the outer rim right here. So the Ramesses is saying, yeah, there's activity in the outer edge, and it can see it, but it didn't reproduce Ramesses by itself. It didn't reproduce this injection of particles, if you will, into the inner domain. And that was we almost forced that with the ensemble, with the assimilation, essentially. So it does see that activity in the outer region, right? And it actually responds, the Ramesses solution responds to that activity, right? And with the assimilation, we basically bumped the population of the proton so that we can see this injection, essentially. So to answer the question, no, none of the ensemble members have this injection or this type of behavior, but it does see the activity in the outer region, definitely. There's a newer version of Ramesses which has a lot of other features, and I'm trying to update the data simulation to use that newer version and see if that newer version does have this type of injection behavior. So that's something exciting that I'm trying to actually get implemented.
Yeah, thank you.
Yeah.
I have a quick question. How much does your assimilation time cadence affect the accuracy of the result?
Excellent question. So, so the time cadence in here, there's a little bit. So if you look at the results, let me go back. There's a little bit of a lag, and I could see that when I start the data simulation, right? So I'm doing it every 5 minutes, and I don't know if I should do it more frequently. Obviously, the way that I'm doing the data simulation in here, it's a little bit inefficient. Basically, it's all through Python script. So I start the simulation, stop it at 5 minutes, update the ensemble, and then feed that back to restart the Ramesses simulation, right? So I didn't want to make it every minute because this was going to take probably a week.
Sure, yeah.
It would have been better if it were native inside the code instead of this outside entity that is saying, run the model, stop it, let me do the simulation, then restart it, right? So there's this thing, I don't know, you guys can tell me what you think.
I was actually curious about how accurate it would be going the other way if you had a longer cadence in between. You know, how well the model, once it has the initial distribution influenced by your simulation, how well does it track, and how often do you need to update it to sort of keep it on a pretty good track from there?
That's a good question. I haven't thought about making it for, okay. So if I make it for say 15 or 30 minutes, I'll update that cadence every 30 minutes. That's a good question. I haven't thought about it. I remember that when we were discussing how the substorm was behaving, this substorm happens very, very fast. So it's not like a little gradual increase of proton flux. It's very much like an injection, a very fast injection. And we chose 5 minutes to see if we can actually, of course, we didn't capture it, but we wanted to capture that injection, how it behaved. But I haven't considered maybe doing it every 30 minutes or every 15, 20 minutes. That's something that I would like to look at. But yes, to answer the question, I don't know.
Sure. Yeah, I'm sure it depends very much on how quickly your inputs are changing too. So,
yes.
But just curious. Yeah, thank you.
So in here, the model's been driven essentially by the solar wind indices, right? So all of these solar wind indices are input into the model so that it can actually react to the current conditions, the solar wind conditions. One thing that I have to remark is that the model has a bit of a memory of where it is and where it's going to go, but it's a very short-term memory. So within 2 or 3 hours, it's influenced by the local or the actual solar wind parameters more than its previous history. Of course, it doesn't discard the previous history completely, But I would say that the history that influences how RAMCB is behaving is about, I'm not going to say that, oh, this is exact. It's about 30 minutes to about an hour, right?
Sure. Okay.
So that it kind of forgets, like, yeah, 2 hours ago, I don't know. This is what the solar indices is telling me that I have to do. So that's what I'm going to do. And this is why I put this cadence of 5 minutes, because if I put the assimilation very, very long, it's essentially going to forget what happened in the previous assimilation analysis.
Yeah, that makes sense.
Yeah.
Cool. Thank you.
This was a very fun project. And I tried something similar for BATS R Us. BATS R Us is a big model. It's just a really, really big model. And I know that the University of Michigan, I think, is actually right now trying to do data assimilation with BATS R Us. That's incredibly exciting, and I would like to see what they have. One more thing. Okay, one more remark that I wanted to make. I don't know how many of you guys have heard of this Smart Sim. So this is a Jupyter Lab kind of Python notebook. I'm trying to learn it. I cannot say that I know what it is, but essentially the pitch is that this thing, it works like a Python script where you run the model, right? So you run the model, but then you don't terminate it to do the data assimilation. You say run the model, pause it in memory, and then the data assimilation just basically captures the memory of the simulation to do your data assimilation. Then you rewrite back into the memory of the simulation, already still, being live, if you will. And I've seen this model being implemented to this E3SM. This is like a global climate atmospheric model from the Department of Energy. And this was like, oh wait, maybe we can do something like this with this model. But of course, this is all pipe dreams right now because I haven't tried it. But it's a very interesting library, Smart Sim, that I've heard. I'm like, okay, this might be worth looking at, seeing how they do that, how they actually preserve the simulations in memory. So you don't have to have this input-output transfer of information from the simulation and from your data assimilation. You can do it all in memory. So I was looking into it, and I don't know if anybody has experience with this or can comment on this. This is something that
I think Los Alamos is ahead of that. I heard somebody, I don't know if you work with people who more in the computing division, that they came to one, I think it's CEDA or GEM, and they are actually more talking about visualization of ensembles, that they do everything transaction in a memory rather than through the files, because that's really the Achilles of ensemble method, because it produces lots of
it produces a lot of input-output. Yes,
file
and this
IO is really cumbersome. So it's a computing issue is really important. Like when we go to something like a BATS, like a 5 minutes updates, like, oh my God.
Yes, because if this thing, the BATS, when you couple it all with the, RAMCB, ring current, everything, when you have everything, the amount of output that thing, one single simulation, we're talking almost terabytes. So it's like, man, I don't know. I don't know how to do it. I can see that in a big cluster machine, if you can keep the BATS simulation in memory in one of the, say, one of the nodes or two nodes or whatever, and then you can actually mine the data from that memory from those nodes and do the data simulation.
Somehow replace that.
Yes, you don't have to do the input output unless you want to actually get some, visualizations and whatnot. But putting this into an actual file and then do your data simulation so that it can read the file, it's very inefficient. So anyways, that's one comment that I wanted to make.
It's very exciting though, but it just I think your approach makes sense to do the analysis in a reduced space, and then as you have mapping to the full space, so that you can actually implement the time update as well. And then congratulations, success on this. Like, it looks really fun.
Because just a very brief note is that the first thing that we tried for this model was this LETKF, the localized ensemble Kalman filter, right? That was a very obvious candidate because it had all the whistles and everything to do the localization and everything, right? And when we tried that, we did get a good track of where the observations, but we didn't get anywhere near where we wanted it to be. So that's why we're saying, are we missing something? Is there something that we're missing when we do the assimilation? And one of my colleagues here in the statistics department said, maybe you have to project this thing into where the ensemble is varying the most. And that's when we said, okay, I mean, I'm only giving you, after a year, like research, I'm only giving you the success, not like the 10,000 failures that we had when we're trying this thing. So, but yes, thank you very much. I don't want to take too much of your time. Thanks.
Great. Yeah.
I'm gonna stop sharing. How do I stop sharing? That's a good question.
I think you're muted, Tomoko.
Oh, yeah. I'm just, yeah. Anthony Adam just, yeah. It's at the top
Okay.
of and then, yeah. Thank you, Humberto. And then this was
Thank
very
you very much.
exciting. And then thank you for sharing your research and then actually good discussion.
Yes. Yes.
Mhm.
Thank
Yeah,
you very
thank you very
much.
much.
Thank
Yeah, and
you.
this will be available on the YouTube channel in a couple days or so too, for anyone that wants to go back and review.
All right. Thanks.
Yeah, thanks everyone for coming. We'll see you next seminar is in February 7th. So we'll see you all
Sounds
then.
Yep. Thank
Thank
you
you.
very much. Have a good day. Bye.
Thank you.
Thank you, Humberto. Awesome.
Thank you.